say. Okay, I'm coming at this from the other direction, but we'll see how this works. I would take 18, 17, and I would dot it with something, maybe, and set it equal to 0. So then, of course, I get a whole range of answers here, right? I get 18a plus 17b has to be 0. So I get a relationship between a and b. That's amazing. So this is at this point, though, right? So then a has to be negative 17 over 18b. Okay, nothing amazing here. Nothing amazing. Just pure cranking it out. Using an idea. It's going to be smallest, of course, when the output is 0. That's the smallest this thing can be. I know it can go negative, but when I say smallest, I mean just pure smallest. Bigger negative, bigger positive, just make it 0. So now let me ask this the other way. Yes.
So that means it's horizontal.
So what's the angle between these two?
90.
Yeah. So what's going to happen? In what way would I move so that it's the largest output?
Horizontal. If they were parallel. So
Yeah, if they were perfectly parallel. I like it.
Equal to
1.
And think about this. If these are parallel, okay, now stay with me. This is the more interesting side. This was easy to do mathematically. So I wanted to ask this question: how do you make it 0? And that, of course, is just make the dot product 0. So then directional derivative is 0. I like it. It's going to be anything that's orthogonal. So it's going to be along this line. Is that cool? If I face those ways, I'm actually. Let me make sure if I can get you guys to go with me. If I face that way or this way, what am I actually standing on? If I start to move in that direction, what am I actually moving along? Because what's happening as I move in that direction? What's not happening as I move in that direction? What did we just do? What did we set this equal to 0, which means what's happening? Nothing's happening, which means the height is not changing at all. And where does the height not change when I'm moving on a level curve? Beautiful. I like it. So this would if I could do this for every single point, I could actually trace out my level curve just by following the outputs of this work. Okay, let me let that kind of sink in a little bit. So we actually sort of had the answer already. But what's interesting is, I love what you just said. It's the exact opposite thing now. This has got to be in the direction of this. If this is in the direction of this, how large will the result be?
1.
No. This has got a length of 1.
It'll be the length of that.
It'll be the length of this. I like it. So the direction of largest increase is the gradient. The gradient points in the direction of largest increase. Notice how slowly I started to talk as I said that last piece. This is on page, where are you at? Yeah, page 992.
It's always going to be a fraction.
So these have to be parallel in order for it to have the maximum output. Since this has got a length of 1, the result will have a length of this pointing in this direction. Yes?
It's maximum increase or decrease depending on what it is, right?
Oh, I'm going to give this up. In direction of max increase. Negative delta f, negative grad f would be the direction of largest decrease.
But if it's like, if grad x was negative 18, negative 17, then it would be a decrease.
Oh yeah, the maximum value could be negative. I'm with you. Okay. So grad f points in the direction of max increase, and the length of grad f would therefore be the maximum slope, if you want to think about that. All right, that maximum derivative, the maximum value. So that gradient vector becomes incredibly important. We're going to use it in quite a few different ways. And a lot of them are going to involve this idea of being able to look at a 2D figure and understand that it represents things that are happening in 3 dimensions. Right? So one way to do that is to look at level curves. And then it's in your face, because you're at 0, and then you're at 1, and then you're at 2, so you must be going up the mountain, right? Or you could do like I'm doing here. I got no level curves here, but I'm still talking about the change in height as I look in certain directions. So now we're looking at our XY plane as something over which a surface exists, but I can still just look at the plane itself and talk about what's happening to that surface. We have to get kind of used to this, or have this ability to talk like that. Let's see. Where do I want to go? Let's do this here. Yeah, well, all right. Let me just formalize a few things I just said here. So this equals this, which equals this. Several different ways to look at it. They all say the same thing, because we define this to be this. This was defined to be this. So sometimes we look at all these different ways of saying the same thing, and we can start to get confused that there's different processes and there's different things to use. They're all the same damn thing. So the book represents this in all these different ways. There was one other thing the book... I can't remember. Oh, okay, cool. Maybe. So I can extend this. Hopefully this makes sense. I can extend this to be true for... Make sure you guys really get what this means. How many total variables would be involved in this? 4. I like it. There's 3 input variables, or otherwise known as 3 independent variables. And then there's 1 that I would consider to be dependent on these 3. Now some of you guys, please realize you can always solve for another one of them and say, well, that's the independent variable. And those are the independent, these are the... Who cares? There's always going to be 1 independent, 3 dependent. So this is 3-dimensional, this is now 4-dimensional. Oh shit. But it's still the same thing. So now I can have some arbitrary 3-dimensional direction that I want to go in and see how this changes. So I could have 3 dimensions being the physical 3 dimensions, and then a 4th dimension being the temperature as I move in that space. So I can say, how will the temperature change as I go in this 3-dimensional direction? Are you guys with me on this? So that's not, it doesn't have to mean 4 physical dimensions. It could mean 3 dimensions, and then something changes as I move in any of the 3 possible dimensions. Are you guys kind of, yes?
You can have basically directions mixed with variables like time, temperature.
Totally. Yes, yes. One of them could be time. That's often thought of as the 4th dimension. But temperature is also a very good one for a 4th dimension. You can have a heat map of something, 3-dimensional space, so that the color becomes that 4th axis, right? Okay, so this doesn't have to mean 4 physical dimensions, thank God, because that's 3 is hard enough to graph. Let's see, I don't want to get too deep into that. Let's see. So let me ask you this here. Let's do this here. Let's take one right out of the book. Yeah, here we go. So given this, Find the maximum rate of change. Of f and the direction in which it occurs. And by the way, I mean, this gradient, the maximum rate of change will always be positive or 0, because the minute you have a negative rate of change, then just look the other way, and then you have a positive rate of change. Do you guys get that idea? This is something semi-new to us, because in Calc 1 even, we didn't normally look both directions unless we were doing some limit from above and below, right? When I said derivative, we only thought about this way. We talked a little bit about if you change the limits of the integral, it becomes the negative of what it was. But we didn't talk too deeply about what that really meant, necessarily, depending on the teacher you had. But now we have all these freaking directions I can look in. I can look in every freaking direction along this circle in the plane. Shit. So it doesn't make sense that if there is a direction where it's a negative change, the opposite direction has to be, I must be going back up the mountain if I turn around. All right? So how do I find, what are you guys doing to find this? How do you do this?
Do you take two partial derivatives in terms of x and y, and then you get the gradient?
Yes, because the gradient, which is fx, fy, is where what happens? That's the direction of what? The gradient tells you the direction of what? Greatest change. I like it. The gradient by itself, and unless the function is remarkably disgusting, even then, derivatives should be something we can just chew up and spit out. Right? You guys have got to be like, please let it be a derivative, not an integral. Right? Derivatives are easy compared to integrals. Integrals get hard quick. Derivatives should be very easy related to it. So it's really easy to find fx, fy. At a point, plug them in, and then that is the direction that I would head in from that point to have this largest increase. So this would be a good thing to know if I can map out, if I have several variables that go into my profit for a company, and I'm like, how do we want to change the all these variables? Part of it can be amount of storage space, another variable could be the price of the product, and another variable could be the amount spent on marketing, whatever freaking variables are in these, because I suck at business, but oh well, that sounded good, didn't it? I could say, what can we change, what changes can we make in these things so that we have the largest increase in profit? Doesn't that sound like something we could do if we had that function to work with? And of course, as a financial analyst sort of does that. He's got a lot of freaking software that does a lot of it for. I'm thinking about a friend of mine, he's a financial analyst, so he does this stuff, right, with software. But that's basically, partially what they do is they do this kind of thing.
Big deal.
Oh well, yeah, one of two colors. So what is the gradient for this going to be at 4, 1? What is grad, let's just do grad f. So let's just do fx. What's fx?
4y.
2y over
Rad
rad x. I like it. So 1/2 comes down, we go to negative 1/2. Blah, blah, blah. Inside's nice and x, right? So what is fx at 4, 1?
1.
1. So what's fy?
4
That's the nice one.
root x.
Yeah, 4 rad x is just the coefficient for y. So that's the derivative with respect to y. And so fy at 4, 1 is just
Negative 8.
square root of 4 is 2 times 4 is
negative.
8. I like it. Sorry. Choo choo. So now my gradient. So when you hear the word gradient, I want you to immediately think The components are the partials with respect to that component. So the x piece is fx, the y piece is fy. If there's a z piece, it's fz. If it's w piece, it's fw. However long it goes. So then the gradient of f at 4, 1 will be 1, 8. Cool. So do you see how that is, it's got a direction and it's got a length, like any vector does. The direction of this vector tells me what? Mike, are you laughing because this is something we just said a minute ago, or are you laughing because you're like, what the hell's going on? Direction of maximum increase. So if I'm standing at the point 4, 1, I have to go in this direction to have my height change the increase the fastest. I like it. I like it. I like it. The length of this. What is the length of that?
Not 3. Oh, 64.
64 and 1. Square root of 65. I like it. Just 13 times 5. Who cares? And that would be the actual value of that biggest increase. So that is the most you can increase the height from this point. So if you're standing on a mountain and you want to have a tougher experience than this, and you're standing at this point, it's too damn bad for you, that's the hardest ascent you can have. You with me? I don't want to be hard, I want to, screw it. All right. Go over there and then you go straight up, or even straight back. Wow. Yeah.
So the red 65 is the max rate of change, and then that's the direction.
Exactly. So if I'm looking in this direction, this is how much the height will change with a step of 1 in this direction. That's what this would predict. And of course we know the minute I say that, you all should understand, the minute I step away from that point, everything changes, depending on how funky the function is. Right? But that's what all the tangent stuff tells me is going to happen from this point. Yes?
So the coefficients, not the coefficients, the components of the gradient are each based on a step, like one step in the x direction and the y direction, right?
Yes.
So if you go 1 in the x, you can expect about 1. And about
So you can scale them down as much as you need.
So, yeah, you can scale them down, but how does the magnitude of that give you one step in the grad direction?
So you got to be careful now. These are, let me try to fully, oh, you're wondering, so if you step in the direction of this,
Yeah.
this is how much it'll change by, right?
It
Oh, you're
seems
asking
like
why
it's
is
step
it
by
one
yeah.
step, and then it would be one step? Is that what your question is?
I just can't quite put it together.
How do I want to say that? So of course this is kind of like the reverse of what I just said. So you can scale down, but when we do something like this has been scaled up for us in a way. I'd have to scale back down to get the real picture, but no, I know what you're asking. I don't know what to tell you right now. I can think about it.
Because it just seems like it would give you the diagonals would be root 2, you know? Almost.
No, I know what you
Or
mean.
Not that, but you know what it
Yeah. No, I got to think about it. I like to do that kind of problem. If you had me for Calc 1, anybody have me for Calc 1? Yeah, some of you guys are like, yeah, I remember this. And I like to do the problem like the stalactite problem.
Yeah.
You guys remember related rate. So what I love to do, and my students, I don't know if you got my point with this, but I always hated the disconnect you had when you did those kind of problems. What the hell did all this shit mean? So I always like to do a problem where we did so the stalactite got longer by a certain amount over a certain given time. So I'd say calculate the volume. Calculate the volume at 5 months, calculate the volume at 6 months, and then calculate the derivative, the rate of change at 5.5 months. You guys kind of with me? So then I could then backtrack and say, did it change by the amount that your derivative work predicted it would change by? I mean, that's a really nice, concrete step to that kind of problem that's not often done. So you're talking about, so I think I'm going to try to, so I can't remember if I've done this before or not. Maybe I've made a problem, I have to look back, about the similar kind of thing with this. Like actually step in this direction and see if it does what it's predicting. So we could do
Well,
that.
that's not what I mean, though.
But no, it's sort of like what you mean, because you're talking about if you step only in this direction by one step, it's supposed to change by that much.
Right.
One direction, one step in that direction, is supposed to change by that much. So why should it be one step in that diagonal, that in between direction? Why isn't it an adjusted step size, right? That's your question. Okay, good. So I can make a problem that kind of analyzes that a little bit deeper. I like that. Cool. Okay. That was it for that section. So if I ask you which direction would I go for the steepest descent, which direction would I go for the steepest descent?
-1,
Yeah, -1, -8. You gotta love that shit, right? It's the same thing I had up here earlier where it was one direction or the other. Had to be the direction to go in. I like it. I like it. Okay, so one little thing, I love that a decent number of you guys got the bonus question correct about finding the critical point. I didn't even ask you if it was a min or a max, because that would have been a little bit much. But, so there's a bonus question on the test. If you didn't try it out, you should look at it, because it's actually remarkably easy problem. What you had to realize was, to be the true max, then that means the slope has to be 0 in every direction, right? So if it's 0 in the x direction, 0 in the y direction, then it's going to be 0 in every direction, because then that plane is going to be parallel to the xy plane. So how does that relate to critical points in two dimensions? Calc 1 is they have to be parallel to the x-axis, right? So now the plane has to be parallel to the xy plane. That's what I call a horizontal tangent plane, just like a horizontal tangent line. Oh shit, there are analogies. I like it. So to find a critical point, just in case you weren't able to do it, example 1 was actually exactly the question on the bonus part. Example 1 from section 14.7. I just took that one. If I have this here, this will be almost too nice. So what's fx here? Negative 2x. And what's fy? 2y. So if you set each of these equal to 0, you force them to be 0. Now, of course, here we get nice, easy answers. X is 0, y is 0. So at the point 0, 0, at the origin, this thing is going to have a critical point. Will it be a max or a min? How do you think you could check that out?
Go 1 unit out.
Check the rates on both sides on the x and the rates on both sides on the y.
You could, yeah.
Second
You
derivative.
could. You have, so you could either do like we did before. You couldn't really do an easy first derivative test and analogy here, because you remember the first derivative test was you make the number line, and then you analyze the rates of change on both sides of the critical point. Well, is there a both sides now? Here's 0, 0.
You do both sides in the x and both sides in the y.
You could, yeah.
Right.
But technically you'd have to do,
Yeah.
So that could get kind of gross. So thankfully there's a really nice, let me say this correctly. It's not the nicest thing in the world, but I do have a handout, and I do have nice explanations about why this is true. But you can kind of pre-read page 1001. We're going to go over what's the second derivative test looks like in this 3 dimensions that we live in now, right? But the nice thing again is there's a lot of analogies between what we're doing now with what we did back in Calc 1. If there's a first derivative possibility, there's a definite second derivative test process that you can go through to analyze this to see if it is a max or a min, or if it's just nothing, if it's one of those haha points, right? I like it. Cool. So that's going to be section 14.7. That's going to go by decently quickly, hopefully. We'll see. I want to let us out of here a little early, because my whole time today was getting ready for you guys, so I haven't done shit for my next class. So yes, you got a question? You good? Okay. Are you guys good with that? I think you guys are okay with that. All right. Yes.
Will the second derivative test involve fxx, yy, and fxy?
Maybe. Read 1001 in the book. Yep, page 1001.